to announce Masato Tsujii from Kyushu University of Japan. He is going to speak on resonances for geodesic flows or negative curved manifolds. Please.
Thank you. I feel very...
You came from a beautiful city.
Sorry?
Kyushu.
Yeah. Thank you. I come from very city in Japan called Fukuoka, and that city is quite close to here, Korea, and I feel at home here. Okay, and I feel very honored that I can give a talk here in this special occasion. And taking this chance, I would like to present my recent joint work with Frederick Faure in Fourier Institute Grenoble. And I'm going to speak about the property of flow, non-singular flow, and we consider spectrum of transfer operator. After I started this kind of study maybe several years ago, and okay, we consider the transfer operator. Transfer operator is just an action of flow on the function on the phase space. Okay, so flow, non-singular flow is just a translation along the flow direction. So basically it is a very natural idea that we restrict the function of the, decompose the function with respect to the frequency in the flow direction. Actually it cannot be done in a compact manifold, but basically it is possible. So we decompose function with respect to the flow, frequency in the flow direction. And we just consider restriction of the transfer operator to each frequency. Okay. And what I found in the beginning is that if we restrict the action of the transfer operator for functions with bounded frequency in the flow direction, then after basically essentially this is equal to the case where case of Anosov diffeomorphism. So before starting to consider flow, actually I worked on Anosov diffeomorphism with Vivian. So I'm very privileged, and actually I think I understand that part. So the problem rest is a case where the frequency goes to infinity. So the situation I have to consider is the following. So we have a function on the phase space which have very high frequency in the flow direction, and it is pushed forwarded by the flow. And we look what will happen. Because there is a complicated dynamics on the transversal direction, things are not simple. Okay. And then my big idea is that, okay, this situation is somewhat similar to the situation considered in the semiclassical analysis. Okay. So I started to go on this idea and start my journey. Actually, this journey took maybe 5 or 6 years. It becomes a very long one. But what is very nice for me, maybe lucky for me, is that I have got a friend. So this is my co-author, who have a background in the semiclassical analysis and physics. So our background is really complementary to each other. And we go on a trip, our journey, and maybe we got some result, and we bring back. So I like to present some of them. Okay, so let me start to introduce some definitions. We consider basically hyperbolic flow, but more specifically a geodesic flow on negatively curved manifold. So geodesic flow is a flow which describes motion of a free particle on the Riemann manifold. Basically, we consider closed manifold, and so things are like this. So particle goes along the geodesic. And okay, so it is basically Hamiltonian flow, and the phase space is the cotangent bundle of that manifold. But in each energy level, actually the dynamics is completely or essentially same. So we restrict ourselves to the unit cotangent bundle or unit tangent bundle. Okay, there's a Riemann matrix on this equilibrium. Okay, and it is very well known in the society of dynamical system that if the manifolds have negative sectional curvature, then the flow is an Anosov flow. It is quite classical. And also, I would like to add that this is a contact Anosov flow. Contact implies that it preserves a contact bound form on the phase space. In this case, this is just a canonical bound form on the cotangent bundle restricted to unit cotangent bundle. Okay, and okay, dynamically it implies that joint non-integrability or completely non-integrability of stable and unstable foliation. Okay, maybe we come back to this point later in the proof part. And we consider the transfer operator. What is transfer operator? This is, okay, defined in this way. And suppose that GT, let us forget about this GT. Then this is just a push forward by flow. And then we introduce this multiplication factor so that makes things more interesting. And, okay, we put this additional condition on this multiplication factor so that this is a one parameter group. Okay, so this is a very natural condition, and this is sometimes called cocycle condition. So this is a completely local operator. So if a function is localized around the point x, then its image by LT is localized around ftx, so its image. Okay. And I want to ask the question that what is the spectrum of the transfer operator, or actually I want to ask you about the question in the generator. Okay. Of course, the question answer depends on the choice of the function space. If you consider, say, L2 space or L1 space, you will not, you will get some result, but you will not get a very detailed property of the flow. So we have to choose the function space carefully to get good information. Okay. And I want to give one preliminary result. This is not our result, but this holds for not only for contact flow or geodesic flow on a negatively curved manifold, but it holds for any smooth Anosov flow. So we know that actually the generator of the transfer operator have discrete spectrum in the following sense. So if you set up some nice function space, here we call BR, and R is one parameter, and then we can see that actually the generator of the action of transfer operator on that space, A, have discrete spectrum in this region. So C depends on the that coefficient and also for flow on the flow. But anyway, this is a constant. And chi0 is a hyperbolistic exponent. And we can choose our arbitrary line. So actually this region, this is a right half plane, but we can make this as large as possible, as we like, by choosing large r. And in that region, actually we only see the discrete eigenvalues. So discrete eigenvalues with finite multiplicity. Actually, I think this kind of discreteness of spectrum is recognized by some researchers in dynamical zeta function, maybe long ago. But precise statement like this is obtained rather recently by in these works. Okay, And I want to emphasize that these eigenvalues are intrinsic to the transfer operators. I mean that the situation is like this. So if we fix the family of transfer operator LT, then we get countably many discrete eigenvalues on the complex plane. And if you choose BR like this, then we observe some part of eigenvalue, the part of those eigenvalues in this region. And if you let R large, then we observe more of them. And finally, if we let R to infinity, after we observe everything. Okay? So this is a situation. And this is, so with these discrete eigenvalues does not depend on the choice of the function space finally. And they are called real polycot resonance of the transfer operator. Okay. And our main result is about the structure of those real polycot resonances. What we found is that they have some band structure, which I described just now. So, okay, this is not very important, but I have to put this. So, suppose that epsilon is a small number, given epsilon number, then the real polycot resonances are contained in some union of zonal region like this. So this zonal region is parallel to the imaginary axis. Okay, I will give a picture in the next slide, but let me state this. Okay, and we consider the union. So after in the next slide, we observe that there are a few zonal regions, and there is some gap between them. And most of the real polycot resonance, actually, so up to finitely many exceptions, and maybe the number of exceptions depend on epsilon, that okay, up to those exceptions, the real polycot resonance is contained in this region. And the band for each band is given by this number. It is a bit complicated. Maybe let me explain a bit. So dt is a coefficient. So it appears naturally. And this is an important factor. This is a determinant of the differentiable flow restricted to EU. So this is a volume expansion rate. And here, this is a minimum expansion rate along the unstable direction. And this is a maximal expansion rate. So basically, chi k plus is bigger than chi k minus. And also if k gets larger, then this number gets small. So, okay, this is a structure. So the claim of this theorem is illustrated as follows. So there's a few bands like this. And maybe most of the case, if this number k becomes large, then these bands intersect each other. So it gives one right half plane. So, but usually we observe a few bands on the right. And also we observe some gaps between them. And actually this structure comes from one structure of transfer operator that I will describe in the proof part. Okay. And this kind of band structure actually is already observed in the special cases when we consider the famous work of Selberg. So Selberg's work is about the surface with constant negative curvature, so for the hyperbolic surface. And in that case, actually, by his result, we can get a complete description of this spectrum. And actually, in this case, these bands, each of these bands are just a line. Okay. And actually, line maybe imaginary axis, and then real part is -1 and the real part is -2. These lines are just these bands. Okay, so basically this is one extension of that's the result in such special case to the general contact analysis flow. Okay, let me continue. There's a few more information on the distribution of the discrete eigenvalue in the band. But for this, actually, I have to assume one condition like this, so disjointness of the band. I think this assumption is not very necessary, but by technical reason, I have to put this now. And so this implies that the rightmost band, so we call it first band or rightmost band, is independent or disjoint from the other band. And there's some gap between these two bands. Then, actually we have some kind of wide law for the number or density of eigenvalues like this. So you go up some value omega in the imaginary direction, and suppose that and count the number of eigenvalues in this interval. Okay, the length of interval is omega to delta. Then the number is proportional. It implies that the ratio is bounded by constant lower and upper bound is given by the constant multiple of this. And here we have this omega powered by d plus delta. So basically the density is omega powered by d. So this is our result. So there are actually many, or countably many, eigenvalues in that band. And the density increase if you go up or go down. And in technical sense, actually this is the most difficult part claim to prove. Usually, it is not difficult to give the upper bound. But to prove the even existence of eigenvalue is not very easy. And so we have to work very hard to get this bound. Okay. And also, if you look inside the band, actually most of the eigenvalue concentrate along the line. And that line is given by this inequality. So chi is a number given by this, and actually this is actually multiplicative. So this number does not depend on t actually, if t is positive. And so this gives one line contained in the band, and actually most of that probabilistic sense. The ratio of the eigenvalue near this line is come close to 1 if you go up or go down along the band. This is a claim. Okay, so my illustration is not very good, but if you look the eigenvalues inside this band, actually it is concentrated along one line, and the density grows like this. Okay, and I want to give one remark about this theorem. I want to consider the first band, so B0. And the bound for that band is given by these two numbers. We drop the last factor. Maybe I don't know if you remember it or not, but there was one factor here, and this is powered by k. But now we consider k equals 0, so we just drop it. And looking at this, then you will find one special case. Do you find it? So if we said that the gt is a reciprocal of this one number, like this, then actually we get, this is a cocycle, and we get that these 2 adjust to 0, right? We don't have to take supremum or infimum. This is always 0. And this is a very special case, and we call this potential as potential lobe reference. So we just give some standard line. And this is rather interesting, so I will give one result related to this fact. This is an interesting case, but one problem about considering this potential is that maybe if you do some dynamical system theory, then you know that this function, or EU, is not smooth. So actually this function is only Helder. So it breaks up some part of our argument. But actually there's some remedy. So this is rather technical part. So here let me just ignore that. So let's suppose that this is smooth. Okay, and in this case we get a very special picture of the distribution of the spectrum. So there is one line, this is imaginary axis, and here there is a concentration of eigenvalues, and there is some gap on the left. On the left there is nothing, and on the right there is gap, Okay, and one related object to that potential reference is the zeta function called what I like to call semiclassical zeta function. Or in physics, it is called Gutzwiller-Born zeta function. It is related to some study of semiclassical study of quantum chaos. And this is defined in this rather complicated form. Okay, let me explain. So here we have exponential, and inside there is two double sum. And one sum is taken over a prime periodic orbit for flow. And the other is just a sum from m equal 1 to infinity. And this factor, so we have m, and this number is just a period of prime period, a prime period of periodic orbit. And d gamma denotes the linearized Poincare map along the flow. Okay? So, and we consider this sum. This kind of sum actually appeared from some consideration of some shredding operator on manifold. But anyway, so one important thing about this semiclassical zeta function is that actually it coincides with the famous Selbach zeta function in the case of constant curvature, constant curvature surface, so hyperbolic surface. In fact, actually we have to slide one half. But anyway, so we know completely about the zeros of Selbach zeta function. So the Selbach zeta function is an entire function, and its zeros are distributed like this. So negative integer, and these eigenvalues are related to the eigenvalues of Laplacian. Okay. So we expect that this is true that for semiclassical zeta function, actually the zero is just a shift of this picture to the right by one half. And okay, then in the field of semiclassical theory of quantum chaos, it is expected that the zeros of semiclassical zeta function is somewhat related to the eigenvalues of Laplacian on the manifold. Actually, we suspect that it is not true or not. Maybe we have to consider some variant of Laplacian on the manifold, but some elliptic operator, which is related to considered as a quantization of the geodesic flow. So this is just an expectation. Actually, I don't know very much about this. Okay, and this is just a background. And one fact is that by using the Attierbot trace formula. This is just a integration of the Schwarz kernel of the transfer operator along the diagonal, defined as like this, and some related technical argument. Actually, the zeros of semiclassical zeta function is related to the discrete spectrum of the generator of the transfer operator in the case of potential reference. This is a very interesting case, and in fact, okay, so there are many technical arguments around it, but in the result we get the following description of the zeros of semiclassical zeta function. Okay, so we can say that this. So for any contact analysis flow, we consider the semiclassical zeta function, and actually we can see that it has a meromorphic extension to the complex plane. Actually, this is not our result. Maybe it is result by recent work of Giuletti, Liberani, and Polygon. And we can say the following for the zeros of this zeta function. So it is contained in this union of these two regions. One is the neighborhood of the imaginary axis, and the other is separated to the right. Okay, so this place. And of course, we have to accept some exception near the real line. So this is unavoidable in our argument. But anyway, we found this kind of structure, and this is basically the corollary of the observation that we made for difference of a potential of reference. Okay. Now I have 20 minutes.
15.
15. Okay. And then I would like to describe the proof of the argument. And especially I want to explain why the spectrum generator of the transfer operator can have discrete spectrum, or why we can calculate the trace of the transfer operator, because transfer operator is usually not compact. So there's actually no legal way to compute this trace, but we like to relate it to the Attierbot trace. So I want to explain how it goes, and also why the band structure comes out. And basic idea is to consider function as a superposition of wave packet, and we consider it as a transformation between wave packet given by the transfer operator. And we describe it to regard LT as a Fourier integral operator. So let me be more precise. So the transfer operator is given by this. So we forget about the multiplication factor GT, because we consider basically high frequency limit. So multiplication by some smooth function is just basically locally, it's a multiplication by constant. So this is actually does not make much problem. So we consider this operator. And as I pointed out, actually this map is completely local. And also, if you consider, okay, this is wave packet. So if you consider the Fourier transform, then, okay, in frequency space, its Fourier transform is concentrated along some number. We consider this kind of situation. Of course, there is uncertainty principle, so it cannot happen completely. But okay, suppose that this is somewhat concentrated around the point C. Then we ask that if you apply LT, then what we get? Okay, the result here. So in the real space, it is concentrated around the point ftx, and in frequency space, should be concentrated around this point. If you consider linearization, it is quite natural. So, and this map is an object that we call a canonical map for transfer operator viewed as a Fourier integral operator. And we consider the dynamics of this canonical map. Okay, let us consider the dynamics. This is actually not so difficult to see. So we have this. So this is time t map of the flow. Anderson flow is not hyperbolic. This is just partially hyperbolic. There is flow direction. So this is a neutral direction and stable and unstable direction. Okay, and note that this central direction is given by the contact form. This is just special in the case of contact Anderson flow. And also, I want to remark that because the frequency in the flow direction is preserved, as I say in the beginning. So actually this flow can be restricted to this region. So for example, if we consider this region XAB, this is also a region where decide whose frequency, the flow direction is in between A and B. So the situation is like this. So there's splitting, and it is not very difficult to see that the non-boundary set of the flow given by canonical maps is just this one. Okay. So in each level we have just a copy of the Anderson flow itself. And outside, actually the dynamics is normally hyperbolic. So if you look at one section around here, you have this picture. So this is just a hyperbolic motion. And so the point comes from stable direction and go out to unstable direction. We have this simple picture. So maybe you are doing dynamical system, then you admit that this wandering part is not very important. In fact, if you introduce this kind of weight function, which decreases exponentially fast along the orbit outside this neighborhood, then we see that we can introduce this kind of function using the non-wandering property of the flow. Of course, it is not possible to do that thing in this neighborhood because this points are non-wandering. Okay, but outside we can do this, and we introduce this kind of weight on the phase space, and actually the space or function we use is defined roughly as follows. We count the wave packet with some weight, and the weight is given by omega WXC that I choose in the last slide. Okay? We count the L2 norm of the wave packet with this weight. Okay, and what we can observe. Okay, so we decompose the transfer operator into two parts. One part concerns the wave packet which is in the neighborhood of the non-wandering set. So the span of alpha. And the other part is the rest. Okay. Then, from the choice of this weight function, actually we can see that this part, L1T, is strongly contracting. And if we consider larger R, then it is more contractive. So basically, we can ignore this part and concentrate on this part. Okay? Let me see again. So basically, we divide transfer operator into two parts. So one concerns the motion outside of this blue region, and one is inside. And the latter is important, and the former is not important for us. And we can make it the latter as contractive as we want. Okay, so and okay, again we restrict ourselves to the some frequency region. So suppose that we restrict LT to the wave packet whose frequency is the flow direction is in between A and B. It corresponds to the fact that we restrict the canonical map to XAB. Or basically this corresponds to the fact to consider the spectrum of generator in this region. Okay. And from the last observation, and okay, now we put this restriction. Then, actually, the first part, which concerns the wave packet around here, becomes compact, because in frequency direction, actually, it is bounded. Also in other direction, also frequency is bounded. So actually, this corresponds to a very smooth function, and the manifold itself is compact. So actually, this is very strongly compact, maybe almost a finite dimension. And this has small operator norm. Okay, and this fact explains why we can have a discrete spectrum, because if we consider the spectrum of generator in this region, actually we only have to consider these two operators, but one is very small and the other is compact. So we have some discrete, some result on the discreteness of the spectrum given in theorem 1. And also, L1T corresponds to this wandering dynamics. So this is, in some sense, non-recurrent. So in calculating trace, actually this is not important or negligible. So we can define the trace of LT as that of this part. So this is trace class, so legally we can define the trace. Finally, we want to describe in 5 minutes that how the band structure of the spectrum appears. So up to this point, we do not use the fact that alpha is a contact form, so no integrability of the form. So here I will use it. So the no integrability of alpha is actually resulting in the fact that this non-boundary set is a simplex submanifold in NTN star, except for the point in the zero section. Okay, and of course canonical map preserves the simplex structure. So actually we can at each point of the omega non-boundary set, we can decompose the tangent space into two directions. One is that along the omega limit set. This is manifold, okay? And this is a symplectic orthogonal. And since the map is symplectic, actually the map, canonical map, preserves this decomposition. Okay. So it implies that basically in the local level or linearized level, this action is decomposed into two pieces. One is along the omega, along the non-boundary set, and the other is the transversal direction. Okay, and here we have to use some idea from semiclassical analysis. So if we have that kind of decomposition of canonical map, then actually the transfer operator itself is decomposed as a tensor product of two operators like this, and each of these have a it is basically very locally. One corresponds to this symplectic map, and the other correspond to this symplectic map. So, sorry, so L parallel have a canonical map corresponding to this V parallel. Okay, so we have this kind of decomposition. And actually, so in the beginning LT, if we look things in L2 norm, actually this is just a unitary operator. And this composition is naturally decomposition into two unitary operators. So nothing. So this decomposition is important, but if you look things in L2, then things are not very interesting. But remember that in the transversal direction to the flow, omega limit, non-boundary set, actually we put the weight WR. So actually, in considering this, actually we can consider the that weight. Okay, and by some small calculation, we see that this operator is essentially same as this operator. This is A is a expanding map corresponding to DFT restricted to unstable manifold. And this is just a L2 normalization of that transfer operator corresponding to A. Okay, and by the effect of that, the weight that we introduce, actually we can forget about the high frequency part. So we only consider the wave packet which correspond to the origin in the phase space. It implies that localized in the neighborhood of the origin, and also its Fourier transform is localized around in the neighborhood of the origin. We consider this kind of situation and this kind of function, and we consider this kind of operation and ask what is the spectrum of that operator. Things are quite simple because, okay, we look things this operator and apply it to very smooth function in the neighborhood of the origin. So we consider just a Taylor expansion. Okay, and this operator preserves the degree of those polynomials appeared in Taylor expansion. So basically, we restrict ourselves this operation to each of homogeneous polynomials, and we, by simple thinking that this operation is more contracting if you consider homogeneous space of homogeneous polynomial with higher degree. So we get some cluster of eigenvalues for this operator, you see, corresponding to each degree of homogeneity. And this is the origin of the band structure I described in theorem 2. So of course, we have to take product with some unitary operator, and finally we have to consider some nonlinearity. So we have to be carefully, but in linearized level, it is completely true. So we have to then we have to work about the nonlinearity. But this is okay. This is hard work, but not very interesting. Okay, I stop here.
Very good, Masato. So we have time for a couple of questions. Please.
I have a question about the.
Wait.
Oh, sorry. Really? I have a question about the sign in the while law. So
yes.
Ultimately, do you recover just the rate of growth of the number of eigenvalues, or do you recover the precise constant? And if so, what is the constant?
Yeah, good question. Maybe I think it's the ratio compared to some constant, and maybe also I think we can make delta to 0. But I I don't know. It's okay. I'm not a specialist about this kind of thing, so yeah, there's some technical difficulty I have. That's all. So maybe it's possible. I think.
More questions or comments? So we thank again. He gets a gift from the organizer, and I hope to see all of you in beautiful Rio de Janeiro in 4 years.